Sucks to be him. All right, let's get through a few more here, and then we'll let you have some work time. And I do have. Has anybody heard of? I'm sure some of you music people have Straight No Chaser. The group Straight No Chaser. They're awesome. Anyway, that was one of their Christmas songs. I thought it would be appropriate. But all right, another one. Let's go through a couple more. Cal, what'd you have?
76.
76, and that was.
The limit as x approaches 0 positive.
From the right.
Okay.
We got you. Sine of x times the natural log of sine of x.
Okay. So 0 from the right. So as we approach 0 from the right, sine would be 0. No. 0. 0 from the right. So sine of 0 is 0. This one's 0. And so we got to kind of think this one through here a little bit. Think of the sine graph like so, right? So from the right, as x approaches 0, sine is approaching 0 from the positive, right? In other words, it's like 0.01, 0.02, that kind of thing. Okay, so then we're talking about ln of values, and here's ln as we approach 0 from the positive. Well, that's negative infinity. So this is a 0 times infinity situation. Okay, so what we would want to do with this, and that's how you do that with a composite function. You can go to do the inside, what's it approaching, and then those outputs are then the inputs for this. So these outputs are the outputs of sine, which are coming down towards 0 from the positive side. So those are the inputs of ln. So we want the inputs to approach 0 from the positive side, and that's negative infinity. So that's the thought process there. Okay? Now what do we do with one like this? So it'd be a little bit like the one we had. I erased it now. What do we do with this so we can do L'Hopital's rule? Bring one down as its reciprocal. What would be the easier one? Sine. Okay? So what I would do is change this to ln sine x over cosecant x, reciprocal of sine. Now what we have is infinity over infinity, because remember, if you do 0 and do its reciprocal, that's basically infinity. So this is an infinity over infinity situation. So we can now do L'Hopital's rule. Okay, so we can do the derivative of the top, which would be 1 over sine, times the derivative of the inside, which is cosine. That's the top. And what's the derivative of cosecant? Negative cosecant times cotangent. Right? So the derivative of cosecant is negative cosecant times cotangent. Now, we're going to now plug a 0 into these. All right? Well, on this one, on top, this is essentially cosine over sine, right? So what's cosine of 0? 1. What's 1 over 0? 1 over something really small. Something really big. So the top here is infinity. Okay, what about this? This would be negative 1 over sine. That's cosecant. And then cotangent is cosine over sine. So if we put a 0 into there, we basically have negative 1 over 0. So we have infinity again. Oh, great. Now, I think we could do some simplifying here. Oh, yeah. You still have it? I can't remember. There were several. Was it a link to the site? Because there was a 1 minute and a 9 minute and when it showed it. Yeah, I'd be at 1:30. Be good. All right. So we got infinity over infinity. Now, actually, there's something I probably should have done before I even did all that. There's some simplifying I can do here. Because what's the top? This is cotangent. This is cotangent. So this is 1 over cosecant. What's 1 over cosecant? And there's a negative on it, right? So this whole thing just simplifies to negative sign. Okay? Because the cotangent divided by cotangent cancels and the reciprocal secant is sign. So negative sign, and now we can put our 0. Sine of 0 is 0. Okay? So you had, but again, the key was in the beginning, and so that's one of the harder ones. Obviously, some I think are going to be easier. You don't want to overthink some of the really easy ones, the one that just high powers dominate or easy L'Hopital's rule. And then there's going to be others where you really got to kind of think it through. You have to use all the different tools that we've talked about. Okay, where we talked about, well, this is getting bigger way faster than this, or this, if x is going to infinity, then certain things will matter, certain things may not. Those can all be tools to use. It's not all L'Hopital's rule. That's just one of the tools we have that we can do these limits. Okay, we talked in the other class. This might be a good time to talk about this again. I think I kind of said this yesterday, but it might be good to revisit. When do limits not exist? When do limits not exist? Well, one time would be the type we did in chapter 2. When you get this kind of a thing. Well, how are you going to know that you have that situation? What's the function going to look like? Piecewise, right? So we're probably not going to get into those on this one. We've already done some of that. We have those problems where when is a function continuous? Well, it's going to be when they meet, right? And when those two are the same. So it's going to be a piecewise function. The cars wouldn't meet, right? So the limit doesn't exist there. So what would you do? You do the left and the right limit, right? That's our directions. If the limit does not exist, tell me more. Check the one side of the limits, that kind of thing. All right? But the one we'll probably run into that's like that is the vertical asymptote situation. Again, the cars don't meet. Well, why is that? Well, because from the left and the right, it goes towards infinity. That's the situation where we have like 4 over 0. So that's probably the more common one you're going to run into now. On this quiz will be the situation where you get something over 0, and then you have to check the left and the right, and they're probably going to be infinity or negative infinity is what you're going to be running into. And there's probably one, maybe somebody wants to ask about one like that. And then the other situation where the limit does not exist is this situation. When you're doing x goes to infinity, and you have a graph that does this, right? Well, this graph, as x goes to infinity, goes to infinity. It does not exist. But we'll go ahead and say infinity is our answer. I would like for you to say does not exist as well. But it just goes to infinity. Remember, for the limit to exist, it has to approach a number. The output has to approach a number. Here, the outputs don't approach a number from each side. Here, the outputs don't approach a number. And here, the outputs don't approach a number. Not as you go way out to the right or way out to the left. Okay, those are the situations where a limit does not exist. Okay? All right. What else? Another one there? Was there one of those vertical asymptote ones? Yeah, Robbie.
I don't know if this was, but number
80?
80. Yeah.
Limit, what does it say? X approaches
Pi over 2.
pi over 2.
So it's looking for these pi over 2 minus x.
Pi over 2 minus x.
Both of these
Okay. All right, this is going to be another one of those kind of 0 times infinity situations. Now, the reason, it'd be nice to know that tangent graph looks like this, and it's got this asymptote, and then it goes like so, and there's a whole bunch of those. And at pi halves is where it has an asymptote. So what's happening is x approaches pi halves. Okay, the tangent graph is going to infinity or negative infinity, depending which side you're on. So this is a 0 times infinity situation. Now, if you didn't remember that, then you could think of this as sine over cosine. And what's the sine of pi halves? Well, that's 1, and the cosine of pi halves is 0. So this is 1 over 0. So if you thought of tangent as sine over cosine, plugged in your pi halves, you get 1 over 0, which should make you think of infinity. Remember, we said that yesterday. 1 over infinity is like 0. 1 over 0 is like infinity. Okay? 1 over something really small. So it's a 0 times infinity. So a good thing to do would be to flip one of these down there. Which one would be an easy one to do? Tangent would be an easy one to do. So I would take this and write this as this. Okay, so this is going to be very much like the one we had just a second ago on number 76, I believe. So we're going to write it this way. So now we have a 0 over 0 situation. Since tangent was infinity, its reciprocal would go towards 0. right? If tangent's getting really big, its reciprocal is going to be getting really small. All right, so we've got that. So we do L'Hopital's rule, which would be the derivative of the top, -1. What's the derivative of cotangent? Negative cosecant squared, which is the same as the reciprocal of sine. So this would be, and they're both negative, I believe. So this would be positive sine squared. This would be the same as that. And now we can put in our pi halves. Sine of pi halves is 1. Squared is 1. So the answer there would be 1. Okay? So these are some of the trickier ones because you do have some manipulating to do to make L'Hopital's rule work. A lot of these are the 0 times infinity situation. Yeah, Cam.
So I did this in a different fashion, and it's probably not right. I probably just got lucky, but I had the same answer.
Yeah, it could
so
be.
Like, it's 0 and infinity, but I just kind of thought of that. I think of it as sine over cosine.
Uh-huh.
Like 1 over 0, and then like the way I did it, 0 times 1 is 0, so that makes it 0 over 0. So instead of flipping it around, I just did the derivative of the whole thing,
Yeah.
which gave me sine squared cosine.
Okay, let me see if I'm following your thinking. So if I make this sine over cosine, then this becomes this times sine all over cosine, like that. Did you do L'Hopital's rule? Are you saying you did L'Hopital's rule on it, or
Yes.
because right now you've got 0 over 0?
Yeah, but like I thought, I think it tangent as sine over cosine.
Yeah.
But I didn't switch it out as that.
Okay,
So like I had 0 times the fraction 1 over 0.
right.
And I had that 0 over 0. So then I just L'Hopital's rule. I guess
Oh,
I see what I did wrong.
you might have just got lucky.
I used L'Hopital's rule over that whole thing, but it's not a fraction, so you can't.
so you're saying like this,
Yeah.
and now as x gets close to pi halves, this is 0, this is 1 over 0. And you did L'Hopital's rule
And I
just on
said
this.
that was- yeah, but I left this tangent using L'Hopital's rule because that was easier. And see, you can't do that because it's not a fraction. But when I did it, I had secant squared.
Yeah, so you're thinking of that to get this. Here's let me see if I find it. You thought of it this way to give you that. Then you said, well, I'm going to do L'Hopital's rule on that, but that was just, so then when you do L'Hopital's rule, you just thought it was tangent.
So I had
The
negative
derivative of that is secant squared. So what you did was a derivative of this, which is -1, tacked it onto the derivative of that, which gave you this, which is the same as this, right? If you put pi halves in there, though, cosine of pi halves is 0.
Yeah. But I guess I did L'Hopital's rule again.
So maybe you did it again.
I remember probably it.
But if you do it again, to what? What'd you do?
Well, because, one.
To this?
Yeah. To that. So when I get negative sine squared of x, so the negatives cancel.
Yeah, but it's not. See, because cosine squared x is cosine x squared. So if you do the derivative, that would be all that. So I think you're right. I think the first thing you said about getting lucky, because there's a lot of stuff that's kind of illegal there. Yeah.
You criminal.
Because L'Hopital's rule is only f prime over g prime. It's only derivative top, derivative bottom. I mean, I'll play the song again for me if you want. I mean, derivative of the top, derivative of the bottom. So that, yeah.
Yeah, you
For
should play
Alex?
the song
Oh.
for me.
Yeah.
Are we still recording for Alex?
We're recording that. Yeah. Well, we can play a song again. I do have that other one I'm going to play. I just think that's cool. But, all right. What else? Now, one we have not done, and maybe nobody needs help with one of these, but maybe I'll just do it because I like to practice them. So if I had x minus 3 over x minus 2, just do that one. As x approaches 2. Okay? So you would do what? Just plug in a 2, right? And when you plug in a 2, you get negative 1 over 0. So then what? Does not exist. And don't quit, right? And now you say, okay, why doesn't it exist? And we go back to what we were saying back here. It can't be this because it's not a piecewise function. It must be this, right? It's a vertical asymptote situation. So on the left, it must be doing like an infinity thing or a negative infinity. Maybe they're both going to infinity. Maybe they're both going to negative infinity, one or the other. It doesn't matter. There's infinity involved somehow whenever you get this number over 0. So it does not exist. We got to check the left and the right. So we go 2 from the left. We go 2 from the right. And the way we do that is we just think of numbers just left of 2, like 1.999. 1.999 minus 2 is a really small negative and getting smaller. You know, somebody called me on this in the other class. They said, well, wait a minute. If you do 1.999 minus 3, okay, that's about negative 1, right? Close to negative 1. We call it negative 1. And 1.999 minus 2 is a really small negative. He said, but isn't that just a number? And that's true. It's just a small negative. So why can't you get a number answer here? You got negative 1 divided by another number. And he was right. I wasn't doing a very good job explaining that. When I say small negative, what am I really saying? Getting smaller and smaller and smaller and smaller, right? Towards 0. Okay, it's not just a small negative number. It's small and getting smaller. That's the key because its x is approaching 2. So I'm getting 1.999999999 and keep getting closer and closer. So as this keeps getting smaller and smaller and smaller, this whole fraction keeps getting what? Bigger and bigger and bigger, eventually to infinity, right? And it's negative divided by negative, so it would be positive. So it's positive infinity. So that's why this is positive infinity that we write here. Okay, this one, when 2 from the right, the top is still about negative 1. But 2 from the right is 2.0001 minus 2. So it's a really small positive and getting smaller, but still staying positive. So negative 1 divided by a really small positive is really big negative. So negative infinity. So this is your justification for why that limit does not exist. Okay? All right. So that's a part of this that I want to make sure we're good with. Yes, Keith. No, I think if they both ended up being positive infinity, could you have said up here that the answer is infinity? Yeah, I mean, that'd be okay. I think in most circles that's acceptable. I just want you to understand that technically that still means the limit doesn't exist. But yeah, I think if they're both, now, you know, that's only if, let's make sure we understand it. If both of these are positive or both are negative, then I think it's reasonable to say, hey, you know, this goes to infinity, which means as x approaches 2, both sides are going to infinity. So I would accept that. But I'd still want to see this, right? I'd still want to see it down here. So, okay, I think that's a pretty good representation of what we have to do for this. And what I've got, so back to the quiz tomorrow. I don't know. Had I mentioned there's a quiz tomorrow? What?
Nice.
Okay. This is some other stuff we did out.
Look, did you see my autobiography quiz?
Here. Okay. So, Saltfield, draw and match. So be able to look back at those old packets we did the other day where we did that. Newton's law of cooling, there's going to be one of those. Now you just basically have to know this formula right here is essentially what you have to know. I'm not sure you need to know right now this difference equation that much. I mean, if they ask you about the rate of change or y prime, you can always do the derivative of that equation. So really the solution here is what you really need to know. And then all this stuff on limits. Anything from the homework today, section 4.2, those homework questions. And yesterday's, I guess, the 2 days we did 4.2 homework. any of those types of questions. Most of those were just limit questions. Okay? So, I'll go ahead and hand this out in case you're not interested in listening to music. You'd rather just work and have a lot of fun, really, I guess.
Yes.
What's that?
Lots of practice, and if you don't quite understand, you look at the book. Look what I learned how to do. Instead of learning how to do limits.
Is that polar? Is that polar?
Yeah, it's a
Polar coordinates?
Well, if we had a quiz about how to make shapes on the photograph.
I would totally ace that.